Hello and good morning everyone. So welcome back to Computer Organization CAC 112. So we are in section A and we are going ahead with our third lecture. So far we have looked into the organizational or the logistics part of the course, followed by the motivational aspects of why we need to study computer organization, and in that process we have also learned or we have gone through few interesting concepts like Moore's law, how computers have evolved, etc. We will continuing this discussion, and we will go ahead and see some more important aspects of computer organization in today's lecture. So the agenda for today will be as follows. So we will talk about processor performance trends, which we started looking at in the last lecture. We will continue that discussion. We will also look at why the design trends or architectural trends have changed somewhere in the year 2000. Followed by that, we will get introduced to what do we mean by instruction set architecture, and from there we will try to understand what are the different nitty-gritties of instruction set architecture, what are the different ways instruction set architecture can be. After that, we will look into the different elements of computer and how we can design a practical computer. So that's the agenda for today. So let's jump into the topic and start with the processor performance trends. So this we have seen in the last lecture, and this is actually showing the performance. This slide is showing the performance of the processors as we go from as we progress in the evolution of computers. So the y axis here is logarithmic, and it shows the performance which is normalized with a very popular computer of very initial days, which is named as VAX 11, and the performance of all the other processors are basically normalized with respect to that. And as we see that with passing years, the performance of these processors have increased quite significantly. So this uh, uh, plot looks linear, but since this y axis is exponential, that means the growth has been exponential, and this is also very much visible from this that we were successfully achieving almost 52% performance growth every year for quite some time. So mid 80s to early 2000. So that's a huge performance gain. And in this plot there are 2 points which are kind of interesting, and we have briefly talked about it earlier also. So in this point, RISC processors were introduced. So RISC is reduced instruction set computing. As we will be discussing about instruction set architecture today, we will go into a little more detail into what do we mean by RISC. So and the introduction of RISC actually made the hardware more modular, more streamlined. You could implement better pipeline strategies because of the uniformity which RISC provides. So in RISC, the most of the instructions are of, or all of the instructions are of same pattern. They have same number of operands, they take same amount of time to get executed, etc. So you can implement parallelism pipelining much better in RISC compared to the counterpart, which is CISC. CISC is complex instruction set computer, and Intel x86 VAX, these are CISC processors. So, anyways, we will go into that in detail in our subsequent slides. Now, as we so this thing was going very well, we progressed very well, but in the last class we discussed that because of the power wall problem, so most of the performance benefits were coming from the fact that we could put more and more transistors inside the chip, and then the architecture was being able to utilize all these transistors by switching them faster and faster. So, if you observe carefully, the clock frequency at which these processors were operating were significantly becoming higher and higher. So, here we see tens of megahertz, here we see 500 megahertz, here we can start seeing around 1 gigahertz. So, basically 1 gigahertz, 1.3 gigahertz and so on, 3.2 gigahertz and so on. But somewhere around early 2000, it was observed that we can't just arbitrarily increase the clock frequency of the processor any further, because of the kind of power dissipation the processors were experiencing, and the density of power was really so high that the normal cost effective cooling mechanism, which uses, let us say, forced air cooling, will not be sufficient to cool the processor enough. So, we also said that the primarily the power dissipation was coming because of the dynamic power, and dynamic power is proportional to basically there is a formula. So, I am not writing the whole formula, which is called alpha CV square F. So, here okay, let me just mention it. So, alpha CV square F. So, basically dynamic power depends on this factor is called activity. So, how frequently or at what portion of your clock frequency you are or the transistors are switching, then the capacitance which the every switching activity needs to charge or discharge, and V is the basically the voltage swing. So, basically every time you switch from one state to another state, what is the voltage swing you go through. So, basically if you have a processor which works at let us say VDD of 1 volt, then the voltage swing will be 0 to 1. So, whenever you switch from on to off, basically earlier it was 1 volt across the switch, and now you will move to 0 volt across that switch or capacitor. So, basically this is the voltage across the capacitor which you are charging or discharging. And then this is the important factor, frequency, and this frequency is what we have been seeing here. So, 500 megahertz or 1.3 gigahertz, and we can see that the power dissipation is directly proportional to frequency. Since we can't do much about the other factors, so this was only and most of the performance was we were getting because we were running things faster and faster, but then we no longer were able to run it any faster, because then the power dissipation was becoming too critical. So, around 2000 the problem was partially addressed by the introduction of many core or multi core processor. So, the idea is that okay, you can't run a single processor at a higher speed, but what you can do, you can run, since you have more and more transistors, can you build multiple processors in the same chip and run them at a reasonable speed and distribute your work among those processors. So, that is the way the multiprocessors came in picture, and yeah. So, this is how the multiprocessors came in picture, and though the hope of getting higher and higher performance was more, but because of several reasons, and one of the primary reason is that you can't parallelize all your programs that easily. Basically, you can't distribute a thread or a single threaded program into multiple threads very easily. There are certain applications which you can very easily parallelize, but not all applications have that kind of capability to, or that easy to parallelize. So, that was one of the reasons, but still nonetheless we have seen that there is lot of multi-core processors around, and we are seeing also reasonable growth. So, though we are not getting 52% per year growth, but we are almost achieving like 22% growth per year for last several last decade or so, and we are continuing this performance, and there are many innovations which are coming to basically help us in maintaining this growth. Now, some of you might think that why it is so important that we need to get have faster and faster processors. This is very very important because uh, many of the technological innovations or many of the future uh, possibilities lie or will be only realized if this trend of growth maintains. For example, the way we our technological innovations are happening, whether it is autonomous vehicle, whether it is let us say very sophisticated assistance for people who need them, or let us say supercomputing capabilities on our handheld devices, etc., which can help us in different situation, whether it is related to healthcare or some other well-being related situation. All these innovations will be only possible if we can maintain this growth, and many of these innovations are relying on the fact that we will have faster and faster computers going forward, and that is why those solutions will be feasible. So, that is why it is very important to maintain this growth. All right. Now, just to give you a very quick overview about where we are in terms of many core systems. There are you might have already realized that from your laptop to your mobile, every processor is now multi-core, because as the problem has been mentioned that we can't run single processors any faster. So, to improve performance, you increase parallelism and you divide the task into multiple processors, which is now an accepted solution, and we have almost all products coming up with multi-core wherever that kind of processing is required. There are many interesting products which are still not that visible in the market. For example, Tylera, right now this company has been bought by another company called EasyChip. They were one of the pioneers who designed processors with hundreds of cores for different applications, from networking to cloud computing, multimedia applications, etc. This processor Epiphany from Adaptiva is a co-processor for a mobile device for gesture recognition, and it has almost 64 cores. Similarly, Intel has their first lab prototype which could sustain 1 teraflop performance with 80 cores. Fortunately, I also worked on this project during my PhD, and then there are other single chip cloud computers from Intel again with 60s or hundreds of cores. So, we see that though we in our consumer level devices like laptops, mobiles, we see let us say maybe 4 core or quad core kind of processors, but in the server level there are many core processors already available, and initially the predictions were that number of cores will grow more rapidly, but there are many challenges associated with it. Some of the challenges many research groups are working on and we are also working on are related to how you share the how you optimally utilize the shared resources. So, one of the primary shared resource in many core processors is basically the memory and then interconnection network. So, how do you manage all those shared resources optimally? That is one of the biggest challenges. Then other challenges like how do you maintain coherence of data among many cores, etc. So, because of these challenges, the growth has not been that drastic as was predicted some time back by the founder of Tylera. He is also a professor at MIT, Professor Anant Agarwal. He kind of proposed a corollary to Moore's law, which said that the number of cores will double every 18 months. So, and that has not happened in true sense, but if we can address many of these challenges which we are I just mentioned, maybe in future we will be in a position where the number of cores will become more and more very frequently. Just to give you a sense that all these things are how practical, how real these things are, just to get a sense, we can look at the way the compute performance has increased in past years. For example, the first 1 teraflop processor which could sustain 1 teraflops floating point operations was designed in 1997, and the it was a huge computer, was taking a big room, complete big room, and it had 72 cabinets. But if you see less than 15 years down the line, in 2011, the same performance was achieved by a single chip processor, Knight's Corner, which was designed in 22 nanometer, and it was a single chip which was almost around 20 nanometer by 20 nanometer in size. So, you see that there is a huge jump in performance which we are getting at a very rapid speed. So, it will not be very not very kind of optimistic to say that we will have server like performance on our handheld devices very soon, and the kind of supercomputers we have today, which are, let us say, sustaining almost exascale performance, maybe 2-3 decades down the line we will have our handheld devices sustaining that kind of performance. So, that is very difficult to visualize, but the way things have been in the past, we can easily assume that this kind of possibilities are pretty real, and if we all work towards achieving that goal, we should be able to get basically achieve those goals. Now, one thing I would also like to highlight here, while many of these kind of performances were achieved, a significant innovation or significant contribution came from the material science. Moore's law helped a lot in achieving this kind of performance, but as we are aware that Moore's law is kind of now slowing down, if not completely irrelevant, it is slowing down now. So, because of that, the other abstraction layers now has to contribute more to achieve this kind of performance trend. So, as a engineer who is aware of computer organization, computer architecture, you guys will have lot more opportunity to address some interesting challenges, so that we can sustain this kind of growth, because we can't expect huge amount of growth coming from the lower abstraction level very easily. So, as we will be focusing on this computer organization, maybe we can propose some interesting solutions there to make this kind of trend possible. All right. So, that pretty much concludes our discussion on the state of the art, the where we are, why computer organization is important. All right. So, as always, I will pause for a moment, and if you have any questions, I will be very happy to answer. All right. Okay. So, now we will move ahead and look into some more basically we will dive into the actual content of the course now, and we will start looking into how a computer is basically instructed to do something. So, by our I am sure all of you intuitively know that computers are not going to understand the language we speak. So, it has to be given very clear crisp instructions to get the get whatever we want to get the computer we want the computer to do, and for that we have to write our instructions in a particular format, and the instructions should be also written in such a way that we can understand what is written. So, though our computers can understand only ones and zeros, it is not a very good idea to write the program in ones and zeros, because then we will not be able to understand what this program is supposed to do. So, so what we do, we write our programs in some high level language, so which are very close to English, and but it follows some very streamlined grammar or syntax, so that there is no ambiguity, like you can only ask the computer to do a particular task in a certain way, and those high level languages like C, C++, Java, Python, you guys are already familiar with. So, these are instructions which are which we can understand easily by looking at the code, and then we use some kind of a translator which we call compiler, so that that high level language can be converted to stream of bits which the computer can execute. Now, during this translation, the compiler actually plays a very important role, and it compiler, or some case it will be interpreter. So, basically there are some there are different ways this program can be translated. So, let us now focus on compiler only. There is another way of translating which is called interpreter. There are different languages, some interpreted languages, some compiled languages. So, we will focus on compiler at this point. So, the compiler basically compiles the code and makes it a provides a binary which the hardware can execute, and then the processor executes those instructions and gives you an output. All right. So, this is how a program computer executes a program. Now, this compiler, it has to know what are the capabilities of the hardware for which the code is being compiled, and that is where the concept of instruction set architecture comes in. So, the compiler has to know what this ISA is. So, what does this ISA specify? So, the ISA specify that like when you do some, let us say, arithmetic operation, where from the operands come. Let us say I have this arithmetic operation a plus b, all right. Now, when I need to execute this, so I will have an ALU inside the processor, so which is called arithmetic and logic unit. So, we will go into the details, but I just wanted to giving you some hint or some heads up about how the what is inside a computer. So, now when we design this or what is there inside this ALU. So, can I directly put my operands which are, so my objective is to add these two numbers. So, somehow these two numbers has to come as the two operands of this ALU, and I have to tell the ALU that you need to perform an addition operation, and let us say I will get the answer as C, all right. Now, there are different ways I can put the operands. So, one way can be these operands are directly coming from some memory. So, I have a memory location, I specify that okay, these first two locations of the memory are my always my operands. So, what I have to do? So, the compiler, whenever it gets this instruction that add these two numbers and store it in C, so first thing it will do that it will take these variables a and b and store them in these memory locations, right, because the ALU will by default take its operand from these two memory locations, and then it will send an instruction that add, and maybe the result, let us say, come back and get stored in this top level memory location. So, if this is my hardware, or this is how the computer gets executed, the program gets executed, then the compiler should know this and accordingly translate the program. So, basically first it will take two variables a, b. So, it will store the first variable in this memory location, second variable in this memory location, and then instruct the ALU to do the addition, and the result will by default get stored here, and then it will display the content of this memory location as your output, all right. So, the compiler needs to know how this hardware is designed to execute this thing. So, this information and many more information will be stored in your instruction set architecture, or basically this is what the instruction set architecture will tell you. So, it basically at a very broad level, it is the semantic of all instruction supported by the processor, and it includes the semantic of the instructions themselves. It will also tell about the operands, and also it tells about the interfaces with peripheral devices. So, basically if you need to connect a peripheral, where the peripheral gets connected, and so on. So, this is a very top level definition. We will keep revisiting this. So, do not worry if everything is not clear yet. I will also spend more time on highlighting the difference between instruction set architecture and organization in our subsequent discussions. So, for now let us take this that the nitty-gritty is about how the operands will be treated, or how the operands will come, how the operands will be where from the operands will come, and all these things which the programmer needs to know, or the compiler designer needs to know. All these things will be defined by the instruction set architecture, all right. Okay. Apart from that, the instruction set architecture will also talk about your how interrupts will be handled, how what will be the basically width of your word. So, basically the number of bits you can parallelly work with, that is defined as your word length. So, what will be the your word length, all these things will be also not exactly word lengths, basically the kind of data you want to you would be able to deal with and their sizes. For example, whether you will be able to deal with floating point numbers, and if so, then what is the how many bits you will be using to represent those floating point numbers, etc. Those will be also defined by instruction set architecture. So, example of instructions in an instruction set architecture are arithmetic instructions like addition, subtraction, multiplication, division, etc. all kind of arithmetic instruction. Logical instructions like AND, OR, NOT, NAND, and so on, and the data transfer and movement instructions like move, store, these kind of instructions. So, basically you load data from memory and store it somewhere and all these things. So, these kind of instructions are also, so all kind of instructions are part of your ISA. Now, what are the characteristics you should be looking for in an ISA? So, ISA should be designed in such a way that you should be able to write any program. So, as a programmer, if I choose to use a particular ISA, I should not be restricted that, oh, I can't write this kind of program using this ISA. So, basically the ISA should be complete. It should be able to implement all programs that users may want to write. Now, that does not mean that ISA has to contain all sorts of instruction. For example, my ISA might only have arithmetic instruction add, and now if I need to do multiplication, what I will do, I will add multiple times to get the multiplication done. So, in that sense, even if I do not have a multiply instruction in my ISA, still it is complete, because I can get the work done maybe in a different way. So, that should be the objective of or characteristics of ISA, that it should be as complete as possible. All right. Okay, so what are the other things the ISA should be maintaining? So, other things should be the ISA should be concise, it should not be too large. The instructions should be of limited size, so that it is manageable. Otherwise, if you think of it like if you have a very large ISA, then think about the complexity of the compiler, because the compiler has to map everything on the hardware. So, if it has a huge subset of or huge set of instruction from which it has to map, the complexity becomes very high, and when you have lot of instructions. So, remember that ultimately this instruction has to be encoded in some binary form. So, if you have, let us say 5000 instructions, or let us say 10,000 instruction compared to 1000 instruction, the number of bits required to denote your instructions will be much more in case of 10,000 instruction compared to 1000 instructions. So, that has many other implications, your program length becomes longer and all these things happen. So, you do not want to build make your instruction set too large. So, typically an ISA will contain anything from 32 to 1000 instruction. So, lower number of instruction indicates that it is a RISC computer. So, RISC, as the name suggests, it is reduced instruction set computing. So, basically you will have less number of instructions in RISC computers. The other feature the ISA should have, it should be generic. Like you are not supposed to write very specific instructions. So, one example here can be, let us say you really do not want to have an instruction like add 14. So, whenever you need to add 14 with some numbers or some variable, you use that instruction, but that will be a very specific instruction or specialized instruction, right? Why do you want to use such kind of a specialized instruction? Rather, you should have an add instruction which takes two operands and add those two operands and stores the value. Now, those the operands can be any number, it can be 14 or any other number. Then you have this generic instruction, add instruction, which can take care of lot more scenarios compared to just a very specific instruction like add 14. So, you do not want to really propose very specialized instruction in your ISA. Also, the ISA should be simple, and this is very important, because if you have a complicated ISA, your organization or microarchitecture becomes very difficult, and that is why I just want to again highlight that CISC has a relatively more complicated ISA compared to RISC, and that is why you saw in that plot where we plotted the processor performance trend. When the RISC was introduced, the processor performance steadily increased significantly. Because of that simplicity of the ISA in RISC, you can really optimize your hardware much better compared to a CISC processor. So, this is very important. So, now so we come to that RISC versus CISC. So, you have different choices while you designing an ISA. For example, how many instructions should you have, what should they do, what kind of task they should do. Do they do only generic task, or they can do some specific task as well, and how complicated they should be. Depending on these factors, these two kind of ISAs are available. So, if the answer to this question, how many instructions should you have, if it is low, then you are talking about RISC kind of processors. What should they do? Should they do generic operations mostly and not at all any specific kind of thing? Then again it should be RISC. Whereas, if you want them to do largely generic operation, but very specific operations also you want to do using your ISA, then the answer will be CISC. Now, you guys might think that what kind of situation or what kind of situation will require let us say some specific instruction. Now, again as we discussed earlier, computer architecture is more or less basically it is about trade offs. So, let us say in your kind of operation, you know that you need to use, or you need to do some kind of floating point. Let me think about it. Let us say you need to in your program, you need to do some kind of a sorting operation, all right, and you need to do it very frequently. So, you have an array of numbers and you need to sort those numbers very frequently. Now, you can think of having one single instruction which says that okay, the input to that instruction is an array, and you say that okay, sort this array, all right, sort this array. And if you need to do this operation very frequently, possibly you want to have an instruction itself which will, in one instruction it will get the work done. So, you will just say that okay, sort array A, and the array A will be sorted in a specific order, ascending or descending order. Now, this is a very specific instruction, this is not a generic instruction, and whenever you write this instruction, you think about what all will go behind or at microarchitecture level, what all tasks will be performed. So, at microarchitecture level, you will first read the whole array, and then whatever you otherwise would have written in the code or your instructions, that thing will be done in the background. Now, to get this work done in the background in the microarchitecture level, your microarchitecture needs to be complex enough. Whereas, if you do not have a short kind of instruction in your ISA and you need to do it through your code only, then your hardware remains very simple. You compare one number with another and then you do it in the code, that you run a loop and you say that okay, you compare one after another and sort them in the code. So, that way your microarchitecture remains very simple, because microarchitecture still needs to do very basic operations like compare and move kind of things. Whereas, if you do this short kind of instruction, then the microarchitecture needs to be complex. So, this is a trade off. Now, you can say that okay, if my application requires this short instruction very frequently, then there is I have not much option but to have that instruction. So, this is a choice we need to make, and that is where this x86 processor as well as lot of RISC processor, they do coexist. There are advantages of CISC type processors and there are some disadvantages as well. Similarly, RISC has their advantages and disadvantages. So, just to again highlight the difference between RISC and CISC. RISC is a reduced set instruction set computer, implements simple instructions that have simple and regular structure. Basically, all instructions will have same number of operands, they will take same amount of time to or same number of cycles to get executed, etc. And the number of instructions are also small, in the range of let us say 64 to 128, and example ISAs are ARM ISA, IBM PowerPC, RISC, RISC-V, etc. All right. So, RISC-V is another processor which is becoming very popular. So, those who want to explore, do let me know. I can provide you some links, very interesting links about this open source ISA. And I need to mention this here, that RISC-V is also adopted as kind of by Indian government, the choice, the ISA of choice of Indian government for future developments, etc. So, it's good to know. It should be always very helpful to know about this ISA in detail. Now, the other type of ISA is CISC, complex instruction set computer. It implements complex instructions that are highly irregular, take multiple operands, implements complex functionalities, and the number of instructions can be also large, typically 500 plus, and there is not much regularity. For example, one instruction might have 0 operand, another instruction might have maybe 5 operands. So, so the hardware or the microarchitecture becomes very complex there. When we will see that how this instructions gets executed on the hardware, we will be able to appreciate why the hardware complexity increases in case of CISC computers. The examples are Intel x86, then VEX processors, etc. So, to summarize what we have discussed so far about the ISA and in general the computers. So, the computers are becoming very fast, but they are basically dumb machines, but they are very fast and becoming faster and faster, but we need to utilize them in appropriate way to get our objectives fulfilled. Instructions are basically very simple commands used to communicate what we want the processor to do, and a computer can execute billions of instructions per second. The compiler basically transform a user program into a high level which is written in high level language like C, etc., and it transforms into a machine instruction which the computer can execute. And the instruction set architecture basically refers to the semantics that helps this translation, or basically the it codifies how the or what kind of instructions will be supported by the hardware, and theoretically tells the compiler, designer, programmer that these are the capabilities of the hardware which you are dealing with. And now these instructions instruction sets or instruction sets architecture needs to be complete, so that they can execute most of the or all the programs which the user or programmer needs to run. It is also desirable that it should be concise, generic and simple. All right. So, this is what we have discussed so far. So, I will stop again for a pause here a bit and wait for your questions or clarifications. All right. Now, let us look at how a computer actually looks, the hardware part of it. So, things will be more and more interesting as we go forward. So, we have already briefly talked about that the computer we are dealing with in currently, it has this stored program model. So, basically you have a memory where your program as well as the data is stored. So, basically memory we can think of an array array where our data is stored. So, one part of this memory is storing our program, one part of that memory is storing the data which needs to, where we needs to where we would like to work put our operands, etc. Now, then there is this important part of the hardware which is called central processing unit or CPU. Now, what does this CPU has? CPU will primarily have a ALU or arithmetic and logic unit, which is used for doing all mathematical operations like mathematical and logic operations, and basically the capabilities of this ALU will define the ISA. For example, if the arithmetic and logic unit can handle floating point operations, then the ISA will reflect that. If it can't, then your ISA should not have floating point operations. Then all the other, like let us say compare function, then increment function, all these things will be done by your ALU. Then there is a very important unit which is called control unit. It will become even more apparent why this control unit is very important. So, I can just highlight one simple fact. Let us say I have this ALU and ALU can take 2 operands at a time. Now, my arithmetic and logic unit can do several different operations. It can do add, multiply, subtract, logic operations, it can do compare operations. Now, the control unit will tell through some select line or some kind of control signal, which will tell that okay, the operands A and B you have fetched from this memory or to execute this instruction, they need to be added or they need to be subtracted. So, the control unit will tell or give this information. Similarly, in a bit we will talk about that many a times these ALUs ALUs have some very fixed ways in which the operands need to be fed to these ALUs. So, for example, it can be such that you have 2 dedicated memory locations, or let us say we call it registers, which where the operand needs to be loaded. So now the operand can come from different locations. It can be from your memory, it can come from some other register, or it can come from some, let us say, some other places. For example, if it is let us say you are comparing your operand with whether it is a negative number or a positive number. So, you will have to compare it with, let us say, 0. So, if it is less than 0, then it is a negative number. If it is more than 0, then, or basically equal or more than 0, then it is a positive number. So, then in that case your operand has to be loaded with a fixed number like 0. So, all these, so this operand can come from different locations, or different options are there. So, that will be also defined, or that will be also dictated by the control unit, that this is where you should get the operand from. So, so in the CPU we have these two important units, ALU and control unit. Control unit does many other things. For example, where you basically what is this instruction which you have which you are supposed to execute now, what is it, like for example the control unit will read that okay, this is the functionality. So, it is a multiply functionality. So, I have to inform the arithmetic unit that this is multiply, and accordingly fetch the operands from these locations and so on, and after the work is done, it will be the, again with the help of control unit, the data or the result will be stored in your data memory. All right. Now, there is another module in the CPU which is again very important, which is called program counter. So, what does the functionality of this program counter? So, the program counter tells that where are you in your set of instructions. So, basically the program, your program which you have written starts from a particular memory location, and then you start executing, and then where from the next instruction come. So, the program counter keeps a track of it. So, by default the program counter, once this instruction is moved or basically this instruction is taken for execution, the program counter moves to the next memory location. So, this is the by default, assuming that your program is written one instruction after another, it is written sequentially. So, you have to execute one instruction after another and so on, provided there is no branch instruction. Now, whenever there is a branch instruction, for example, let us say in this location there is a branch instruction, then once you realize that this is a branch instruction, you know that the next instruction is not going to come from this location or the immediate next location. So, you have to basically decode the branch instruction, you have to understand or basically identify what is the location from where the data needs to be fetched and on, and then accordingly your program counter has to be updated, and who will do that? Again the control unit will do that. All right. So, we have a small animation which shows that okay, if this is your program and the program counter basically moves from one instruction to another to tell the CPU that okay, the next instruction has to be fetched from here. All right. So, this is very very important. So, we will talk about program counter in more detail in later as well. So, just to reiterate, we have CPU, it has program counter, control unit and ALU, and we have memory where our program and data resides. So, this is at a very top level how our computer block diagram looks like. All right. So, what are the elements we discussed so far? So, it has memory, so it is arrays of bytes which contains the program, and program is nothing but sequence of instruction that the computer needs to execute. Also, the memory contains the data which the program needs to use, for example, the different variables, the constants, the operands, etc. The program counter points to the instruction, in a program. So, every time an instruction is executed, it points to the next instruction by default, the program counter, and whenever there is a branch instruction, you have to appropriately update the program counter so that it can point to the appropriate instruction that need to be fetched by following the branch. Then there is your CPU, which contains the program counter, instruction, execution unit like ALU, etc. In it. All right. Now, again I will possibly pause here for a moment and wait for any questions if you might have. All right. So, now let us look at a toy example, and we try to design an instruction set architecture. And the unique part of this instruction set architecture, that we want to only have one instruction in this instruction set architecture. But remember, we said that we want that instruction set architecture to be complete. So, we have to select an instruction which is such that it can implement any instruction. So, one interesting such instruction is SBN. So, SBN stands for subtract and branch if negative. So, what this instruction says? This says that okay, you if you have an instruction like SBN, let us say A comma B comma some line number where you need to jump. So, when this jump will happen? So, basically it will perform this A equals A minus B, and if this answer is negative, then it will jump to the line number which is specified, and if it is not negative, then it will go to the next subsequent instruction. And the claim is that if we have this kind of an instruction, then we should be able to implement any instruction. As an example, let us look at this this instruction. So, our objective is to add two numbers A and B. All right. So, how can we do that? Using our single instruction. So, we define a variable, we name that variable as temp, and we initialize that variable with 0. All right. So, we say that okay, first you write this instruction, subtract temp. Basically you do this operation, temp equals temp minus B, and if this result is negative, then you jump to line number 2. So, we have initialized temp with 0. So, 0 minus B, the answer will be negative. So, you will go to the instruction line number 2. So, what is temp containing now? Temp is basically initialized now with minus B. So, the next instruction we will do is basically A equals A minus temp. Now, what is temp? Temp is nothing but minus B. All right. And once we execute this, then we have our addition operation done. We have A variable updated with A plus B. All right. So, now you can experiment and you can look at it for other instruction also. The book also talks about another example. So, where basically summing the numbers 1 to 10 was done using this SBN instruction alone. So, I highly encourage you guys to experiment or basically play with this and run more and more instruction or execute more and more instruction using this single ISA. If we look at a more practical ISA like this multiple instruction ISAs, we need arithmetic instructions like add, subtract, multiply, divide, etc. We need logic instructions like AND, OR, NOT, NAND, etc. We need move instructions like load, move, store, etc. And also we need branch instruction for changing the sequence of execution in the code. All right. Now let us look at how a practical computer looks like. So, a practical computer will have all these components which we have already discussed. So, you have an ALU, so you have this CPU, and now the memory can be divided into two parts. You can have separate instruction memory and separate data memory, and if you have a architecture like this, then this architecture is called Harvard architecture. The earlier architecture where memory was unified, so basically instruction and data were residing in the same memory, that is called von Neumann architecture. Now, in this practical block diagram, what is different? We also have added some IO devices. For example, let us say some of the operands might even come from IO devices. Maybe some user input will be used as an operand, or user input can create some interrupts, etc., which we will talk about in our subsequent lectures. So, I hope this block diagram of a computer is clear, and please remember that by Harvard architecture we mean that the instruction memory and data memory are separate, and we will see also the advantages of keeping them separate when we talk about pipeline. The other architecture which is we mentioned as von Neumann architecture. So, there you have unified memory. So, both data and instructions are in the same memory, and rest of the things are same. So, nothing different, same way the instructions are executed in this CPU as well. Okay. So, there is some interesting aspects of or there are some limitations of this von Neumann architecture or Harvard architecture, where the CPU is directly talking to memory to get their instruction as well as the data. Now, generally memory is large, and because of the physics involved in how the memory is designed, let me very briefly tell you the physical constraints which are there in a memory. I hope you guys can see whatever I am drawing. So, generally what is a memory? So, memory is some hardware which contains lot of cells. So, it is basically array of cells which contains the data. Now, as you want to make this memory bigger and bigger, because you do need large memory to support let us say large amount of data, so that you can store large amount of data, you can have reasonably big program, etc., to run all these things. Now, as you make your memory bigger and bigger, because of the physical constraints, because it will have its own dimensions and all, how do you access the memory? You will have some decoder which will basically enable some rows or some arrow columns, basically where from you can read the data. Now, as this memory becomes bigger and bigger, these wires connecting these different rows or different columns become longer and longer. Now, they introduce physical limitation. So, the time required or the amount of charge required to basically charge these wires or discharge these wires becomes very high, and as a result you can't really do these read write operations very fast in your main memory because of the physical limitation of how the memory is designed. So, what do you do? So, if you use the main memory as we are proposing in the um, Harvard architecture and von Neumann architecture, then your processing will become very slow, because every time you need to get the data from your memory, the processor will be sitting idle, because let us say your processor can work with a speed of let us say 100. I am just giving you some hypothetical situation. So, if the processor can do the task at a speed of let us say 100 instruction it can execute per second, let us say the memory is putting a bottleneck that it can only access one data in that same amount of time. So, even if your processor is capable of doing 100 operations, it will be doing only one operation, because the bottleneck here is the main memory. Bottleneck is the main memory, which can be accessed only let us say once in 100 units of time. All right. So, to overcome that, the proposal is, can we build some smaller memories or registers which will be closer to your processor. Now, what is the advantage of that? The advantage here is that see, it has been observed, irrespective of the kind of application you are looking at, generally there is a very high spatial and temporal locality in the data you access in executing a program. So, what do I mean? I mean, like if you have accessed a data recently, then irrespective of what instructions or what kind of program you have, it is very likely that you will access that same data again. So, that is called temporal locality. So, basically very soon you will be using that data again. Similarly, if you have accessed this data, it is very highly likely that you will be accessing the adjacent data as well. So, that is called temporal spatial locality. So, since we have this kind of observation of both spatial and temporal locality of the pattern in the data we access, it makes sense to have some kind of a small amount of memory which is very close to the CPU, and exploiting this temporal and spatial locality, we can basically populate those small and fast memories with the appropriate data. So, these small and fast memories which are close to the processor are called registers, and we can use these registers appropriately for loading them with the appropriate operands and the data which the program needs, so that they can be accessed very frequently and in a fast pace. So, because if we add this modification, then our processor, okay, let me come back to this. Then our processor CPU architecture looks like this. So, inside now in the CPU you have a bank of registers also, where you can store your operands for easily accessing them for your operations, and that increases the speed of your processor significantly. So, typically a CPU or a processor contains a set of registers which lie between 16 to 64 number. These are also named as storage location. Typically these values are loaded from memory to register, and whenever you need to, let us say, load a new value. So, whatever the old value was, you have to store it back to the main memory and then bring the new data. And typically the ALU etc. directly access these registers, and these registers provide the operands which are required for the ALU etc. So, one example code can be using this kind of registers is that, let us say I want to add two numbers A and B, or rather B and C, and I want to store it in a variable which is let us say A. So, basically our objective is to do this operation A equals B plus C. So, what we will do, we will load B from a memory location in a register file R1, then we will load C in a memory in another register R2, and then the ALU will do this operation and store the values of R1 and R2 and basically store it in R3, and then we store the register R3 in memory location A. So, using these registers, you see this is how we can write programs. All right. So, I hope this part is very intuitive and clear. We have already talked about this slide. Okay. So, I will stop here today, and in the next class we will start from discussing about the difference between architecture and microarchitecture. Thank you.